Okay, so welcome to the Informs QSR webinar series. And today we're fortunate to have Professor Dr. Kamran Paynabar from Georgia Tech speaks on low-dimensional learning from high-dimensional data for system modeling and improvement. So a little bit of background. Professor Kamran Paynabar is a Faust Family Early Career Professor and Associate Professor in H. Milton Stewart School of Industrial and System Engineering at Georgia Tech. He received his PhD in IOE and Master in Statistics from the University of Michigan. His research interests comprise both applied and methodological aspects of machine learning and statistical modeling integrated with engineering principles. He is a recipient of the Data Mining Best Student Paper Award, the Best Application Paper Award from the IC Transaction, the Best QSR Referee Paper from Informs, and the Best Paper Award from Palms. He has been recognized with GT Campus Level 2014 Junior Faculty Teaching Excellence Award and the Provost Teaching and Learning Fellowship. He served as the chair of QSR of Informs and the president of QCRE of IIC. He is an associate editor for Technometrics and IEEE TASTE, a department editor for IIC Transaction, and a member of editorial board for Journal of Quality and Technology. So without further ado, now let's welcome Professor Kamran Paynabar.
Thank you very much for the nice introduction, Yufi, and hello, everyone. Thanks to the webinar committee of QSR for inviting me. It's a pleasure to present a summary of my research in the area of low-dimensional learning from high-dimensional data. And this presentation today is a result of a series of collaborative projects with my former and current students and some of my colleagues at Georgia Tech and other universities. Let me start with the outline. I'm going to talk about the background and how Industry 4.0 can give us some opportunities in terms of data and also challenges in terms of analytics and how this can be translated to research problems. And then I talk about the framework of low-dimensional learning from high-dimensional data. Specifically, I talk about basically LDHD in the context of process monitoring and anomaly detection, process modeling and optimization, process control, and prognostic and degradation analysis. So basically what we are trying to do, we try to revisit traditional quality and reliability problems and in the context of high-dimensional data. If I get time, I'll talk about some potential research direction, and finally I'll wrap up my presentation with a summary. Okay, let's just start with Industrial Revolution timeline. And late 1700, the first industrial revolution happened, and by moving from manual labor to mechanization. And at the time, steam power was the main source of machines, the energy for the machines. And this created an opportunity for significant improvement in terms of productivity manufacturing systems. About 100 years later, the second revolution happened by introducing the mass production assembly line by Henry Ford, and gradually electrical energy replaced the steam power. Fast forward about like 100 years later, we had Industry 3.0 or third revolution, which was mainly due to computer technologies and electronics. So it helped automate the process. The concept of computer-aided design and computer-aided manufacturing were introduced. And again, it created opportunities for more efficiency and faster, higher yield manufacturing systems. And now these days, we hear a lot about Industry 4.0 or the fourth industrial revolution, which is mainly due to advancement in computational technologies and basically sensor technology, wireless sensor, machines can talk to each other, You have sensors that can get the data and wirelessly transfer to cloud, or do the analysis on the local servers or even local devices or sensors at the edge of the manufacturing process. So let's look at this timeline with the perspective or point of view of data. The first two eras that we had traditional data collection, inspection, measurement, test for quality, and it was manual, mostly costly, time consuming, and sometimes imprecise. However, in the past 50 years, especially like during past 20 years, we have significant, because of those industrial revolutions, we have significant opportunities and for in terms of data collection. And the technology facilitated automatic data collection versus instead of manual, inexpensive data collection. It's fast and it's mostly precise. Now, this has created a data-intensive environment, rich amount of data, and some of the examples that Industry 4.0 type of data that we can collect is given here. We can have multi-stream data from the sensor readings, for example, pressure, temperature, vibration, and so on and so forth. They are mathematically represented by a vector, and usually we have the problem of the characteristic of data is autocorrelation and cross-correlation among the sensors, autocorrelation over time. Another type of data collected is waveform signals, profile, and functional data. For example, here you can see during one operation in a press machine, you can record the exerted force, and that gives you a profile. This is represented as a vector, but it's a function of time or a space. They are more kind of like a high dimensional because each data point can be considered as a function. We still have this temporal correlation, but we do have functional structure as well. Another type of data is multi-channel signals, more complicated, and grayscale images, as you can see when you have different channels of a profile. And this data can be presented by a matrix, as you can see here. And in addition to temporal correlation, we can have spatial correlation as well. And finally, color images, color 3D scans, and videos are another types of data, high-dimensional data that is collected in this Industry 4.0 environment. And as you can see, they can be represented by tensors or multiple matrices or high-dimensional matrices. And we do have temporal, spatial correlation, higher order spectral correlations as well. Now, this is the type of data that we have. It gives us opportunity for what? For process modeling and optimization, for monitoring and anomaly detection, prognostics and degradation analysis, process control, and diagnosis and root cause identification. Basically, all the problems that the classical and traditional problems in quality and reliability that we had before, we have opportunities of using this data intensive, the intense data or high dimensional big data to have a better contribution in these areas. However, as you know, there is no such a thing as free lunch. So it comes with challenges, significant analytical challenges due to data high dimensionality, the heterogeneous structure of data. Some of them are profiles, images, videos, point cloud, scalars. Complex correlation in terms of temporal, spatial, and spectral correlation. The need for real-time analysis makes everything, because we know that the data are collected much faster. The sampling frequency is pretty high. So therefore we need, especially for the cases of monitoring, we need to do the analysis and control. We need to do analysis on the fly. So we need to have agile computational algorithms for computational complexity, both in time and space, and also dealing with this data requires interdisciplinary expertise that I explain later. Now, how to address these challenges? There is one common characteristic among all these high-dimensional heterogeneous data that can help us address these challenges. And that characteristic is the essential and important information of this data is embedded in a low dimensional structure. So if we learn this low dimensional structure, then we can basically take this low dimensional structure into account and develop the algorithms that we are interested. So basically we can come up, use this low dimensional learning and come up with a generic modeling framework for high dimensional heterogeneous data. So I want to emphasize on the generic part. When I say generic, it means that it can be used for any types of data that I mentioned earlier. For example, profiles, images, video, point cloud, scalar. Okay, so that's why it's important to be generic. We don't want to develop algorithms for each type of data separately. Now, let's focus on the interdisciplinary expertise part that I mentioned earlier. This low dimensional learning from high dimensional data requires combination of different basically expertise. The classical quality and reliability methods, statistical machine learning is important. Optimization definitely is one important part of it. Signal and image processing, computational engineering, functional data analysis, and I would say one of the most important elements of it is domain knowledge. Like every single problem that we are trying to solve, we need to have some knowledge about the domain of the problem, some expert that can help us analyze data correctly and interpret the results correctly. Otherwise, the conclusions, that the result that we are basically drawing from our analysis would be misleading. Okay, at this point of talk, I'm gonna talk about how this low dimensional learning can be used for different purposes. I start with monitoring and anomaly detection. So let's look at some applications of system monitoring using high dimensional streaming data. There is one example here, as you can see, the valve seat assembly process. You have a press machine that tries to assemble these valves inside the engine head, as you can see. And during each operation cycle, I collect this force profile, and I have different operation cycles over time. So it gives me a series or a stream of these profiles. Same thing happened with multi-channel signals. In the forging basically applications, you have 4 sensors mounted on the 4 columns of the machine. And during each operation, I have 4 channels of the signals. And then I have multiple of those. And I want to use that to monitor the process, for example, to see if there is any missing part in the forging machine. The rolling is another example. We use a camera to monitor and inspect the surface of rolling to see if there is any quality problem or not, as you can see in this video. And if there is any quality problem here, as you can see, we want to detect it. Another example is in semiconductor manufacturing, where we have images of a stress map to detect the location, high stress location and defects. So the objective is we want to develop a real-time monitoring method that can be used for all of these types of data. And it should be real-time in the sense that it can be, the analysis should be done with a very high speed, so we can basically, it should be at the level of the sampling frequency of the data that we are collecting. So the methodology that we are basically developed here, we called it the Spatio-Temporal a smooth sparse decomposition. And so here is how it works. Imagine that we have a sequence of data or sequence of profiles. Here in this case, we have sequence of images, okay? And it's noisy and it may have some anomalies. So we said, what if we can decompose it into 3 parts? The spatio-temporal mean, as you can see, which is a smooth, we assume it's a smooth, as you can see, it's smoothly changing over space and time. The anomaly part, which is a sparse, it's not covering the whole area. And the noise part, which is a small, okay, in terms of magnitude. So what if we can do this basic decomposition? Now, what we can do in order to deal with the high dimensionality, we can cast this problem as a regression problem. So as you can see here, since we know that we are dealing with a smooth spatio-temporal behavior, we can use a smooth basis, like a spline basis, in time and space to reduce the dimension of the problem. And as you can see, the Kronecker product of these two bases can give us the spatio-temporal basis that we are interested in. And for if we have some knowledge about the sparse anomalies, we can also define some basis for that as well. If not, we can just drop that part. Now the problem becomes becomes estimating theta and theta sub a, which is the background and the anomalies. We can estimate these two using a least square problem, penalized least square problem, where we want to minimize the error. And then we have two penalties. You remember we mentioned that we want to have a smooth spatio-temporal mean. So we have a penalty, which is L2 norm penalty, which penalizes the roughness. R is roughness, which is related to the second derivative. So it encourages the estimate to be smooth. And also we have L1 norm penalty, which encourages the anomalies to be sparse. Then we have a constraint which says if when you estimate that, and if we put these together, you want to get your actual data, original data. So how we can solve that? We can solve this using basically accelerated proximal gradient method by Nesterov or iterative thresholding algorithm. There are some computational challenges because the dimension, we have both spatial and temporal dimension. And we need to have matrix inversion, and the complexities of order of 6. Then we, based on using some tricks and change of variables, we can reduce these to order of the cubic order, which is much better. But the problem is not just that. The problem is in the optimization over time. So assume that like we have these 3 sample data. I run and solve this optimization for these 3. Then in the next step, I have another one. So I need to solve the optimization for these 4, and then for these 5, and then for these 6. So as you can see, when I have new images or new frames of data, then I need to basically solve the optimization problem. At some point, the computational complexity cannot be handled by any algorithm. It's going to explode. So what would be the potential solution? The potential solution is we can come up with a recursive estimation framework. What it means? It means that I can use the solution of optimization problem at time t and the data coming from t+1, and using this data, I can update the optimization solution. So that creates a lot of efficiency in terms of optimization and estimation. So under some simplifying assumptions, which is not bad and non-realistic, it's a good assumption. We can show that the solution to the optimization problem along the time direction is in the recursive form. As you can see, solution at time t is a linear combination of the solution at time t-1 and the data at time t. Okay, so that significantly simplifies the computation. So as you can see, this is a kind of like the temporal structure, and this part is the spatial structure. So we are combining both temporal and spatial information to update the solution. And in the space, we can also use the previous algorithms and update the solution. So this recursive updating can help us to analyze the data on the fly. Okay, and as you can see, the computation doesn't depend over the time anymore. So it's fixed, and here we have an index of time, but here we can see it's fixed, and that the main point, an important point for making the algorithm real time. So here is one simulation I want to show you. This is a kind of like a heat transfer process. If you, for example, heat up a steel metal, you can see heat is propagated over the surface. So we are trying to simulate that process, which is a smooth spatio-temporal behavior. And in this basically video, you can see that in this top left corner, you will see original data, which is very noisy. top right, you can see the estimation of a spatio-temporal, a smooth spatio-temporal behavior of the heat transfer process. Here, you can see the detected anomalies, and we have also a control chart. We basically, if we detect anomalies, we feed it into a penalized likelihood ratio test to see if it's significant statistically or not. So when I run it, you can see that everything is fine at the beginning. There is no anomalies, but the spatio-temporal estimation, you cannot see it here, but after estimation, we can see it here. Suddenly we have a defect, we can detect it, and that can be detected here using the control chart. And again, this one is being done in real time. We compared with other methods out there, and you can see it's basically beating all the methods in terms of ARL, but and also in terms of diagnosis, it can pinpoint the location of anomalies as well. And in terms of precision and recall, also it's doing a much better job. And the time is around 0.1 seconds, which allows us again to run this algorithm in real time. Let's look at some case studies. This is the rolling process that I discussed before. So this is the original image of rolling. This is the background, which is estimated. And if there's anomaly, we detect it here. As you can see, we detect some anomalies, and then the control chart goes out of control. As I mentioned before, it's important, this methodology it's not just limited to the videos or images. It can be used for any types of high dimensional data. This is another example that we used it for multi-channel signals in the forging process. So you can see there is basically different operations over time. We have this sequence of profiles, and then there is a missing part at some point, and we can detect that missing part here. And as I mentioned before, we can do diagnosis. For example, here using this heat map, I can pinpoint which channels are more sensitive to that change, and which area of basically signal are more affected. As you can see, channel 1 is more basically sensitive to this change, and it turns out the missing part is closer to this column, which is captured by channel 1. Okay. So here are like 3 examples of how this framework can be used for process monitoring and anomaly detection. The second topic is process modeling and optimization. So in some cases, basically we are interested in finding the relationship between process variables and the quality characteristics of output, okay? One example is in semiconductor manufacturing. This is a sort of like a stage-wise and layer-by-layer process, and each layer we have deposition of some pattern. And it's really important that these layers to be aligned. The misalignment of these layers, it creates basically something called overlay error. And this overlay error can be represented by a heat map, as you can see here. 0 is there is no overlay error, and then the rest is basically we have deviation from that 0. And this can be basically influenced by a series of process variables, as you can see here, for example, deposition rate, temperature, and then pressure, and so on and so forth. Now, these process variables are basically in form of profiles, and the output is in form of images. So both of them are in high dimensional data. The question is how I can find a function which shows the relationship between these two, because later on that function can be used for process optimization or prediction. The second example is a structure of a material. So the microstructure of a material is important, especially in material science. We want to see how in service conditions, for example, temperature, stress, cycle time during the use and operation would affect the microstructure of the material. And that would be important also for not only prediction, but also if you want to do some treatment of the material, okay? The last example is process optimization, parameter optimization. Here is a machining example, and we have in the machining, we are producing, let's say, cylinders, and 2 variables are important, the speed of the machine and depth of the cutting depth. We want to know what is the relationship between the speed and depth, and the outcome is basically the point cloud, which shows the geometrical information or dimension of this cylinder. So there are other examples here, but I escape due to interest of time. But here is the problem that we are trying to model. So we have n samples of training data, and these samples are heterogeneous high-dimensional data. For example, could be images, could be profiles, could be point cloud. And the output is also, could be anything. It could be a scalar, could be point cloud, could be any high-dimensional data. Now, what we want to do, we want to use this training data to learn a function which relates these inputs to output, and then use this function later on, either for prediction or for process optimization. So the methodology that we use here is Tensor-on-Tensor regression. So what is a tensor? Tensor is a multi-dimensional array. For example, a vector is one-dimensional tensor or one first-order tensor. Matrix, two-dimensional tensor, and basically sequence of images is for example, a three-dimensional tensor. Okay. Now, the way that we want to basically model the problem, as I said, is a regression problem. So it's basically Y is a high-dimensional object, and we have a basically inner product of the input and output. I'm sorry, and the coefficient, corresponding coefficient, plus some noise. So basically, this is very similar to the regular linear regression that we have. The only difference is the objects that we have, the coefficients, the inputs could be different. Could be one of them could be image, one of them could be profile, and the dimension of the coefficients are also corresponds to the type of input that we have. So we use a specific type of inner product. It's contraction product or Einstein's product, because we want to relate, make sure that when we do this product and multiplication, the dimension matches the dimension of the output. And that is done by using this product. So this is basic pictorial way of showing this. So it's a regular regression. We can estimate using least square all the betas that we have. The only problem is that too many parameters to estimate. For example, let's say we have only two objects, one input, one output. Object output is image, input is image. Input is 20 by 20, output is 30 by 30. Now, how many parameters we need to estimate using this methodology is 360,000. So there is no way we can do that. So what should we do? Again, we need to take advantage of low rank representation of these parameters. Some of the methods that we can use is tensor decomposition. Here is a Tucker decomposition. So basically, instead of dealing with a very high dimensional beta, we can see what we can do. We can decompose it into a series of factorizing matrix and a small core tensor. So the dimension significantly reduces, and the question now is how I can learn this B1, B2, or factorizing matrices and the core tensor. Okay, and in here in this example, you can see the dimension, the number of parameters that we need to estimate can be reduced from 300,000 to 484 only using this, for example, tensor decomposition. Okay, so how we can include this tensor decomposition into the regression problem. So what we do, we expand our beta based on those core tensors and factorizing matrices. And we try to estimate those core tensors and factorizing matrices using this optimization problem. So these U's are factorizing matrices. V's are also factorizing matrices. One is related to dimension, input, and the other one is related to the output. Okay. Then one thing I want to emphasize here, so we can solve this optimization problem and then get the coefficients. But here is one thing that I want to emphasize here. So one may say, okay, why don't you do that? Why don't you first reduce the dimension of Y and reduce the dimension of X using a PCA or a tensor separately, and then try to find this regression or do this regression or estimation of the parameter in this low dimensional structure? And that is one way to do that, and that's correct. The problem that I have with this low dimensional learning is when we are trying to extract this low dimensional structure, we are not considering the relationship between y and x if we do them separately. But here, we're not only learning a low dimensional structure, but also we're learning the dimensional, low dimensional structure, which is coming from the relationship, maximizing relationship between y and x. Okay, capturing the most important information of y and x, relationship between y and x. Okay, now let's look at the basically case study here, the process optimization. So you remember the input is a scalar, speed and depth, and the output is a point cloud. What we want to do, we want to first learn the A, which is the tensor coefficients. Using this methodology, we can do that. And this is the coefficients for depth. This is coefficient for speed. For example, if depth is 5 multiplied by this basically coefficient, and whatever speed is multiplied by this coefficient, we can get the point cloud, resulting point cloud. Okay. Now, something which is interesting, at the end of the day, we want to optimize the process. And optimization here means that I want to minimize the deviation from nominal values. Okay, so the deviation from nominal values. So as you can see, I want to minimize the deviation from nominal values, the ones that I have from the drawings, okay, from the design. And at the same time, I want to make sure that the variance is less than some desired value. And I know that I have operational range for speed and I have operational range for depth. So solving this optimization problem based on the coefficients that we estimated before, this is the coefficients or the relationship that we found before, we can cast the problem as a quadratic programming with linear constraint, and we can find the optimal settings 80 and 0.825. And as you can see, the resulting basically cylinder is much smoother with less deviation, and we can reduce the shape variation by 65%. If you compare this shape with the one that we have, with the ones that we have here, we can see it has a lot of, we can achieve a lot of improvement here. Okay. Another case study is in material microstructure modeling. Again, we want to find the relationship between input, which is time, stress, and temperature, and the output, which is microstructure. By the way, microstructure is translated using a 2-point correlation, translated to a heat map known as 2-point correlation heat map. So we want to use this information to estimate this heat map. And here is the result that we have. This is the original image, one example. I'm just showing one example. And this is the tensor regression. And this is the PCA method. So if you use PCA instead of tensor regression, you can see there are a lot of subtle variations that is not captured by PCA estimate. However, it's captured by tensor regression methodology. And you can see in terms of mean square error, standardized mean square error, tensor regression is performing much better than PCA. Final example in this area is engine calibration. So the engine calibration in the diesel engine, it's important to avoid pollution to calibrate the engine. One important factor is here is called like lambda signal. The lambda signal, if it's below, it's related to some pollutants. So if it goes below a threshold, then the treatment of exhaust gas has a problem, and the pollution, it's polluting the environment. Okay. So it's basically related to nitrogen oxide, we have different engine variables or sensors that we can use to control that. For example, inner torque, speed, and so on and so forth. So we want to find the relationship between these input profiles and the outcome, which is profile. So in the previous examples, inputs were scalar, the output was image. Now we can see inputs are profiles and output is profile. So we do that, and we can see we can have very nice estimation using this method. And as you can see, the method, the MTOT, which is the tensor regression, is performing much better than basically other benchmarks. For example, partial least square or higher order partial least square or SIGCOMP. Okay. Now, the next topic is process control. In the process control, basically now what we want to do, we want to utilize, so process optimization starts with process modeling. So we find the relationship between input and output, and then we want to optimize it. But this optimization is being done offline. But in process control, we want to do this optimization online, meaning that we have a target and we want to achieve this target over time and by changing some control variables. Okay, so we have two steps. The first step is offline estimation, and the second step is the online control. So the offline estimation is being done very similar to the process modeling that I discussed earlier. However, there is one change that I will talk later, is that offline estimation in the previous case was static, but here now we have the time series data or time series of objects. So that should be taken into account because we have temporal structure as well. And in the online control, we utilize this model and we want to derive a control law which minimizes deviation of the output from the target. That's what we want to do in online control. So the first step is offline estimation. The offline estimation is being done by, again, tensor regression modeling, but now the tensor regression was static. Now we have time series data. So we extend this concept to time series data, and we propose a tensor-based Rmax model, Rmax model, because X is basically the control variable. So as you can see, the Y is with lag of P's related to the previous objects. We have this 8 coefficient to estimate, and we also have these control variables with the corresponding coefficients. And we also have non-IID noises. So the problem is now to estimate these coefficients, okay? And after estimating these coefficients, the second part of the problem is control objective function. We want to find the optimal value of the control action such that this difference is minimized, okay? The quadratic loss is minimized. I don't go through the estimation, but again, it's similar. We utilize the low dimensional structure for estimation. I'll just show you some examples. So here is one example of basically simulation example. The target is 0, okay? And we have a time series of data. We have two cases. One case is that we have a large correlation, spatial correlation, and then the other one is a small spatial correlation. So if you look at the, let me write one more time. If we don't have any control, it starts here, so it never goes to 0. But with control, after a few iterations, it goes to noises, which is kind of like exactly the target would be 0. So it's moving around 0. And we also compared it with the univariate control methods, which doesn't consider the correlation structure. When the correlation structure is low in this case, I'm sorry, is low in this case, in both cases, by the way, proposed method is better. But the significant, the difference is more significant and more profound in the cases that we have higher correlation, spatial correlation. And that makes sense because univariate control doesn't take this into account. So we use this in the semiconductor manufacturing example to control the overlay error. These arrows that you are seeing is a control overlay error. This example is without control. You can see without control, we always have the overlay error, but with control at the beginning we have, and then it vanishes. So we can easily make sure that the error, it's going to be around the target, which is 0. And here is the error for without control case, and this is with control case, which error is very close to 0, the deviation. Okay. The next topic is prognostics and degradation analysis. So far we covered monitoring, process modeling and optimization, and process control. Now, what if we want to do predictive analytics in terms of predicting the remaining lifetime of the basically system? Okay, so it can have, we may have thousands of sensors, hundreds or thousands of sensors on basically aircraft engine, and we want to use this information to predict the remaining lifetime. It could be a profile, for example, a starter profile in the engine. And over time, we want to analyze these profiles to see what is the remaining lifetime of the starter, or we can have the infrared images of the bearing and to predict what is the remaining lifetime of the bearing. So these are all like high dimensional data that we want to use for degradation analysis. So the objective is, if I have a training set of training data, which comes with a signal, and we have the corresponding time to failure, can I use this high dimensional signal and find the relationship between the input and the output for predicting the time to failure? And then later on, you can use, for a new one, I can use this information, update the model and do the prediction over time. That's the objective. So as you can see, this is really similar to Tensor-on-Tensor regression. The input is tensor and the output is just a scalar. So we use a similar approach here. However, there's one difference is because we know that we are dealing with reliability and time to failure. The normal may not be always the case. The normal loss function, which is the ordinary least square. We may use different distributions, for example, log location distributions, log location scale distributions. So we used, or we developed a method, tensor-based. We combine the tensor methodology with log location scale regression model, which is highly used in reliability, and basically can cover a family of distribution like normal, log normal, y-bel, a smallest extreme value, and so on and so forth. So how it works, we say yi is coming from this log location distribution, and the mu, which is the location parameter, sigma is the scale parameter. This mu is a function of the signal and the coefficients. So it's basically, I can represent this mu as a function of the high dimensional data that I have with this basic coefficient. And then again, the question is the dimensionality, and then we can use a similar methodology to do the dimension reduction. However, after doing this dimension reduction should be done in the context of maximum likelihood estimation. So we propose a penalized maximum likelihood estimation estimator here, which is inside is combined with Tucker or CP decomposition for dimension reduction. Okay, I just want to give you the big picture. The mathematics is not that important. The big picture is combining this log location and regression concept with the low dimensional learning. And here is the example, the actual example that we had from the lab. Basically, this is the sequence of images, infrared images for predicting the remaining lifetime of bearing. And we compare it with other methods like FPCA, PCA, B-spline, and this is CP and Tucker, which is our proposed method. Both of them are performing more or less better, especially Tucker is the best in terms of the absolute mean of prediction error and the absolute mean, the variance of the mean prediction error. X-axis is the observed percentile of the lifetime. So for example, 10% means 10% of lifetime has been observed. And the y-axis is the error. So as you can see, Tucker is best. Actually, Tucker is one type of decomposition, is performing better than CP because it has more parameters and it has more flexibility. However, it has more computational basic complexity as well. Okay. So last topic I'm going to talk about is kind of like a different topic. It's not related to images or still is on high dimensional data and low dimensional learning, but it's basically robust prognostic model when we have poor quality data. So the problem is similar. I have P sensors, okay? And I want to use the information of P sensor to predict the time to failure. However, because of some problems, because of data contamination, because of the sensor error, I only observe a subset of those points. So instead of observing the whole signal in blue, I observe only the red points, okay? I have a training data and I want to do the same thing. On top of that, we may have sensor data on the Y as well, because we cannot run the experiment for forever. Okay, so we may have some sort of like a sensor data at different times. Now we want to use this data to find a predictive function that can be used for real-time, the online prognostics modeling and prediction. Okay. So the way that we modeled this problem was using matrix completion. So matrix completion, I can put all these signals together. And if I do that, then I have a big matrix and I have some missing values that I want to estimate, okay? So matrix completion has been used and studied widely in the area of machine learning. And one way of dealing with this problem is matrix factorization. So basically you want to find the factorizing matrix of this incomplete matrix such that the error for observed data is minimized, and you want to make sure that these factorizing matrices are in low rank. So that's basically the objective function for matrix completion. But we don't want to do matrix completion first and then do estimation second, because we know that there is some information between the relationship between Y and S here, which should be used in the matrix completion task. So what we do, we combine the regression task and matrix completion and create a matrix completion in the context of maximum likelihood estimation. So we get a maximum likelihood, a penalized maximum likelihood, which has two parts. The first part is matrix completion, and the second part is the regression part. And we have constraints that shows that we have the sensor data or not. So solving this optimization problem can help us basically not only recover the basically missing observations, but also predict the remaining lifetime of the system with missing data, with sparse signals, the signals with missing data or corrupted data. Here is the performance. As you can see, we have different examples. One of this is kind of like a SDR, which is our method. Matrix completion, do it separately from our method and using B-spline. So B-spline basically is performing the worst, but as you can see, our methodology is better than the two-step approach of first doing matrix completion, then doing SDR, especially in the cases that we have. If you look at this difference, you can see the difference is more profound when we have more missing data. Okay. And then the reason is because SDR is taking the advantage of all this information, the recovered signal itself, other signals from the same sensor, signals from other sensors, and also the information of TTF. So it takes advantage of all these pieces of information to do the prediction and imputation. Okay. Just to wrap up my presentation, we presented a framework of low-dimensional learning from high-dimensional data, both in the static fashion and dynamic fashion for streaming data, and used this framework to revisit the quality and reliability problems such as monitoring, anomaly detection, control, process modeling, and optimization, and prognostics. There are a lot to be done, but this is a basically very I would say the research opportunities in this field is vast, and I would encourage everyone who is interested in that area start working in that area. And one last thing, I want to again emphasize on the multidisciplinary and interdisciplinary expertise that it requires for this field. And I want to say that we need to, so basically that encourages us and motivates us to revisit some of the undergraduate and graduate curriculum to make sure that they can get the interdisciplinary training when they graduate, so they can basically do effective research in their low-dimensional learning and analytics of high-dimensional data. With that, I want to acknowledge my collaborators here. As I said, my former and current student and some of my colleagues at Georgia Tech and other universities. And thank you very much for your attention. And if you have any questions, I will be more than happy to answer. Thanks.
So thanks for the great talk from Cameron. And if you have any questions, feel free to put your question either in chat or just say something, let me know, so I will be able to give you the privilege of talking. Either way works. Thank you.
Hello, can I talk now?
Yes, I can hear you.
Hi, Cameron. Thanks a lot for the amazing talk. Just one quick question. So you have this tensor-on-tensor regression. My question is that what happens if one of my predictors is in terms of a functional variable? And I know that there's a thin line between functional and tensorial, but how would you model this situation? You have a sensor recording the force, for example, and it's a functional relationship. I mean, it's a functional variable. Would you use like functional setting or use, again, a tensorial representation for the functional predictor and apply your method on that in this situation?
Oh, very good. Thank you, yes, sir. This is a very good question. Let me see if I can find it. It actually is here. So this is the setting that you're talking about. The inputs are in the functional form and the profiles, and then the output is also in the functional form. I think in this case, I would say both methods can be used. Okay, they are kind of like using a similar approach. Okay, depending on how to develop your functional model and how to develop your tensor model. For example, if in the functional model, as a matter of fact, let me basically say this first. We solved this engine calibration problem using both functional approach and tensor approach. Okay, so we did that both. The functional approach can be, the result could be very similar to the tensorial approach under some cases and under some assumptions. For example, if you are using the eigenvectors or eigenbases in the functional domain, in the functional regression, the result can be related to the tensor that we use. We learned the basis, low dimensional basis for using the tensorial approach. However, there is another option in the functional regression that you don't use eigenbasis. You use, for example, a spline, or based on the behavior of the function that you have, you may use wavelet basis or Fourier basis. So that would be less relevant because you don't learn the basis in that case. It would be less comparable to the tensorial approach, because in tensorial approach, you learn the basis and the coefficients both at the same time. I would say both methods have their own merits, and both of them can be used depending on the application that you have.
Great, thank you.
Sure.
Cameron, also we have some questions in the question and answer panel. Will you be able to see it?
I don't. Can you read out for me?
Yes, I can definitely elaborate for you.
Sure.
So the first question I got here is from Professor Byung, saying that this is a great talk. Thank you so much. I do have one question. When you explained Industry 4.0, you mentioned the separate physical systems and IoT. So how is your research related to separate physical system and IoT?
Basically, the research that I'm trying to do is like after the fact. Okay, so it's basically this IoT, Internet of Things, and cyber physical systems that machine talks to each other and so on and so forth can give us opportunity to collect the data. Okay, that was the main point. And then my research is more on, if I have this vast amount of data, how can I use that to improve and model the systems? So in that context of how the relationship between machines and sensors and so on and so forth can be used, this kind of relationship can be used for improving or modeling the system. I've not done any research in that area, but I think it's a very important research area that can be used, that require further exploration. But this is not my research. My research is mostly on the data analysis, which the data itself, the data collection itself, is taking the advantage of Internet of Things and talking machines and data collection. And these methodologies can be used both in the cloud setting and in the edge setting. Okay, so I can service this Internet of Things, but that is my main research.
Okay. Then the second question from Dr. Nadakani. Thanks for great presentation, very interesting. I have a question regarding the first part of presentation. So what kind of characteristics did you plot it on the control chart?
The control chart, the monitoring, I would assume that the question is about monitoring. So this one is the detected anomalies, okay? So that would be a low dimension, okay? So I use that as a kind of like a multivariate vector, and then we use a sort of like a penalized T squared, put it this way, to get the monitoring statistic. So instead of monitoring the whole thing, what's gonna happen, that helps us with dimension reduction. We are separating the suspected region, the region that we guess that anomalies can happen, get those low dimensional regions, and then apply a hypothesis testing or penalized hypothesis testing on top of that, which is the control chart. Okay.
Is there any other questions? Feel free to type in the question and answer panel, or just raise your hand and I will allow you to talk. Okay, so if there will be no more questions from the participants, then we'll just end this webinar. Again, thanks a lot for the great presentation, great talk from Professor Kamran Paynabar from Georgia Tech. And you guys have a great night or good day. Thank you.
Thank you very much. Thanks for having me. Have a good day, everyone.
Thank you, Kamran.